Here we'll be looking at parametric techniques that test for variation between independent samples. In other words, we'll be looking at simple t-test and one-way ANOVA. First, you need to make the parametric assumption where the data has to be continuous rather than categorical. The data also has to be randomly distributed. The observation has to be independent. Data has to be normally distributed. And every time you take a sample from a population, the variance will be always the same. To check if the data is normally distributed, we need to create a histogram where, as you can see on the left, where all the data is even but normally distributed, where you can draw a bell-shaped line. So both sides are basically the same. Now you can check which test you can use, either a simple t-test or one-way ANOVA. To know if it's a simple t-test, it has to be you can only test two groups only, where the groups you find a group difference between both, and the participants can only be tested only once. One-way ANOVA is just when there's only 3 or more groups being tested at, and it finds out the difference between all the groups at once, and the samples from the group only be tested once only as well. Here you can see a breakdown graph where you can find out which test you can use. You go check if the data is continuous, if it's normally distributed, if the participants are being used more than once, how many groups are there.
Okay, now we start by calculating the t-value, and that's the formula. S is the mean of sample 1, and S is the standard deviation of sample, and N is the number of individual. And you can see the examples. The examples random sample were taken of plotted in C1 and D8. And you can see there is C1 data and there is D8 data. And defines your hypothesis. Non-hypothesis is mu1 equals mu2, and alternative hypothesis mu1 is not equal mu2. First, we need to work out the mean height for each sample. We can get the mean of sample 1 is equal 161.6, and the mean of sample 2 is equal 168.27. And second, we need to work out the difference in means. Then use the formula, we can get 6.67. And now we need to work out the standard deviation for each sample, and use the formula. We can get S1 equal 10.86 and S2 equal 11.74. Also, we need to calculate S squared divided N for each sample. We can get C1 equals 7.86 and D8 equals 9.19. Okay, now we use the whole formula to calculate t-value, and you can see here t-value equals 1.62. Then now we need to work out the number of degree of freedom. And from the example, it's given that N1 and E2 is equal 15. So we can calculate the degree of freedom equal 15 plus 15 minus 2 equal 28. And now the last part, we need to use the 95% confidence limit to find the critical value in the table. You can see here the critical value equals 2.048 and t-value equals 1.62, and 1.62 less than 2.048. So there's no a significant difference between the height of students in sample from C1 and t-est. So we accept null hypothesis.
Okay, so as you have seen, an independent sample t-test is used to identify significant variation between two independent groups by looking at their means. But what happens if you wish to compare the means of more than two different groups? Couldn't you just do multiple t-tests for each possible group pairing? Yes, you could do, but as the number of groups increases, the number of tests also rapidly increases. And as the number of tests increases, not only do you have to do more work, but you are actually increasing the probability of making a type 1 error, the probability of incorrectly rejecting the null hypothesis by chance. If you have more than two independent groups, one-way ANOVA, or one-way analysis of variance, is a much better test. It can determine whether or not at least two group means are significantly different to each other, and you only have to do the test once. This means the probability of making a type 1 error remains at the initial fixed level and doesn't become inflated. Why is it called one-way ANOVA? Well, analysis of variance is given the name because it compares or analyzes the variation from two sources. There's the between group variation. This is the variance that's due to differences between groups and is gauged by comparing each group mean around the grand mean. The grand mean is basically the overall mean. And then you have within group variation, that's due to differences between observations within groups. This is deduced by comparing each observation with its group mean. The between group variation tends to be due to the independent variable, whereas the within group variation is believed to be due to chance. Why is it called one way? Well, it's called one way because there's only one independent variable, so it only has one grouping dimension. Okay, so here I'm going to go for an example to show you how one-way ANOVA is applied in practice. I've come up with this scenario where you wish to compare the fat content of three different ice cream brands, A, B and C, to gauge whether or not they are sort of equally unhealthy or not by measuring their fat content. One-way ANOVA is an appropriate test to use here because you have one independent categorical variable, which is the ice cream brand, with more than two categories, so you have three in this case. Each category is independent and it's measuring the same response to the same dependent variable, fat content, which is measured in grams, so it's on a continuous scale. And here I've just sort of given the null hypothesis, so you're testing whether all three group means are equal. I've used a 5% significance level, and the alternative hypothesis would be that at least two group means are significantly different to each other. Okay, so as explained previously, if we wish to carry out a one-way ANOVA test and compute an F ratio, we need to first determine the sum of squares for each source of variability, so between, within, and the total. I've begun by modifying the table, including extra columns which contain the square of each observation. Basically, all three sum of squares can be computed by combinations of the following three values. Here you have the sum of each group's total squared and divided by n, where n is the group size. So here it'd be 148.7 squared plus 89.3 squared plus 114.8 squared divided by the group size, which is 7, which is equal to 6,180.75 to two decimal places. You could then calculate another value, the sum of all observations squared and divided by n, where n is the total number of observations. So you'd have 148.7 plus 89.3 plus 114.8 all squared divided by 21, which is equal to 5,927.04 to do decimal places. And then the third value that you need to calculate is the total of all sums of the squared observations. So it would be 3,164.57 plus 1,148.73 plus 1,885.24, which gives you 6,198.54. Having established these values, we can now substitute them directly into the equations for the sum of squares. So the between sum of squares will be 6,180.75 minus 5,927.04, giving the between sum of squares as 253.71. The within sum of squares can be computed as well, so 6,198.54 minus 6,180.75 is equal to 17.79. To be honest, only the between sum of squares and within sum of squares need to be calculated, but it's good to calculate the total sum of squares as a way of checking or verifying that these two values equal the total sum of squares, as they do here. Okay, so having calculated the sum of squares, we now need to calculate the degrees of freedom. So like before, the between group degrees of freedom is equal to k minus 1. In this case it's 3 minus 1, as there's 3 different groups. The degrees of freedom for within group variation is n minus k, where n is the total number of observations. So here we have 21 observations in total, minus k, which is 3, which is 18. And then the total group, well, the degrees of freedom for the total group variation is n minus 1, which is 20. So having found the sum of squares for each source of variability and the degrees of freedom, you can calculate the mean sum of squares. So the mean sum of squares for routine variation is the sum of squares divided by this degrees of freedom. Here it would be 253.71 divided by 2, which is equal to 117.86. And then the mean sum of squares for within variation is equal to 17.79 divided by 18, which is equal to 0.99. Having found the mean, both mean sum of squares for the between and within variation, the F ratio can now be calculated, which is the between, the mean sum of squares for the between variation divided by the mean sum of squares for the within variation, giving a ratio equal to 119.05 to do the decimal places. Having calculated the F ratio, we now want to know whether or not it's significant. And there's two ways of doing this. Here I've done it by the critical value approach. So I've looked at an F table which corresponds to our significance level that we set as 0.05. And I've used the two pieces of information relating to the degrees of freedom. So here the degrees of freedom for within groups is basically the row number, 21 minus 3, in other words n minus k, and the degrees of freedom for between groups, which is 3 minus 1. Basically the entry that you're interested in is where they intersect. So it would be at F218, giving a critical value of 3.5546, and this is by far smaller than the F calculated value, or the F ratio, which was 119.05. So you can reject the null hypothesis and state that at least two of the group means are significantly different to each other.